I'm doing this for the benefit of the video. Okay, so we'll use the board theorem, fine. So 12 here, why the Moore's theorem is going to be cos then 12 pi over 6 by I sine 12 pi over 6. 12 pi over 6 is 2 pi. It's something about 2 pi at sine and cos. Cos of 2 pi is going to be 2 pi to the whole. Yes, it's going to be 1, isn't it? 1 plus 0i, which is just 1 for part A. Okay, so that's part A done. Part B is our proof by induction. So I'm going to do this step by step. Sean thinks he's got it. Sean, he's still on part E. All right, so I'm going to test. There are the last 4, I think. Okay. Test. So we're looking at the base case here when what's the n equals 1, I suppose. Yeah, n is 1, positive integers. It says it in the question. So we'll do that. So cos alpha minus I sine alpha. When n is 1, so 1. Let's just cos alpha minus I sine alpha. Does it hold? I think it does. Yes. And it says the question asks. So therefore, we will assume so it's also called the inductive hypothesis. So we use K. So cos alpha minus I sine alpha will assume for n equal to K that it does work. Cos K alpha minus I sine. Okay, so we'll do that. Now we're going to prove for n equals to K plus 1. Okay, so let's do that. Let's substitute in first. So cos, we're trying to say, will this work out? So sine alpha, cos alpha minus I sine alpha to the K plus 1 now. Will that give? What I wanted to give is cos K plus 1 alpha minus I sine K plus 1 alpha. Okay, so I'm just going to look. But that's going to try. I'm going to work with this. I'm trying to make it look like the right answer of my plan. I'm going to have to use this at some stage. I don't have it yet. So what I'll do is I'll split it up into times K, and then using the rules of indices time to the power of K, power 1. So just switched hands for my proof. So this is just the left-hand side looking at cos alpha minus I sine alpha, the power of K times cos alpha minus I sine alpha. Okay, to the power of 1. So that's fine if you do that. I'm trying to get it to look like this, and I'm going to use the inductive step at some stage. I'm going to use the inductive step right now. Well, I didn't, but I will use it right now in a second. I'm going to say that I'm going to multiply that first and then do it. I could do it now, but I'm going to just. So that's times K to the times the cos alpha part. Then it's going to be minus. Get rid of it. Get a bit long, so we'll just get rid of it over here. Cos alpha minus I sine alpha K times minus I sine alpha. Now minus I sine alpha. I think I've done that. No, that's already minus there. Sorry, I didn't need to put in the second minus. I've already put it. All right, now I'll use the inductive step. So in the inductive step, it says that this thing equals that thing. So I'll use that now. So every time I have this thing, I'll put in that thing. Okay, so that's got rid of our power of k. Of course, there is no power of k, and our answer will be k plus 1. And this is where we're going to get it. We're going to get it from this. And I'm going to remove a bit more so So I've already used the inductive step, so I get that out of the way. I'll leave what I have to prove. So I get to that. I'm going to literally multiply it out now, and then use the angle formulas, for compound angle formulas in reverse. So that times that is cos k alpha times cos alpha minus I sine k alpha times alpha. This times this is going to be minus I cos k alpha sine alpha. And then I'm going to get plus minus. So it's going to be minus I squared. So that's going to be plus. No, sorry, it's going to be it's minus times minus gives me plus I squared. And that's going to become minus 1. So it's going to be back to minus. I could have taken an extra step or two there, but it's going to be sine k alpha. Anyway, yuck. But it's working out, I think. If I group the real and the real, I will be able to, I think, use some compound angle formulas. Back in brackets. So the real bits are cos k alpha cos alpha, and we have minus sine k alpha sine alpha. Okay, that's the real bits. Now the imaginary bits, and that's going to be minus I times sine k alpha cos alpha plus sine. Now, from our formula booklet, we can use the compound angle formulas for sine and cos. So this will be the compound angle formula for cos in reverse, and this is the compound angle for sine in reverse. And that should give us, from this one, it's going to be cos k plus 1. Well, it's going to be k alpha plus alpha, and that's the alpha outside, which is what we wanted. So k alpha plus alpha, but I'll factorize it because that's what we wanted. And this from the sine compound angle is going to be sine k alpha plus alpha, but that's k plus 1. Right, so hence it's held for n is equal to k plus 1. And so I can conclude it holds for n equal to 1, k equal to 1. If the n equals to k, if it's true, then it holds for all. Oh, sorry, no, holds for L in all k element of positive integers because n equals k plus 1, or some sort of conclusion like that. I never write it, so I'm trying to remember it. So. Okay, so is that what you did, Sean? Yes. Okay. No, still not there, but okay, so that was part B, proof by induction. Are you still stuck, Sean? Are you there? Oh. I'll try and get there eventually. All right, awesome. So, oh god, yeah. Part C. So we have W is equal to cos alpha plus I. So I presume you did this fine, Sean. Talk to me about what we need to do. So we need to get. Okay. What'd you do here? Yeah. So what was it? W to the power of n? Yeah. So W to the power of n is going to be cos n alpha plus I sine n alpha minus its conjugate. So that's W with n in it from De Moor. And from the previous part, we figured out you can do something very similar for the minus, can't we? That's just using the previous. Okay, so that's using the conjugate in part B. When minus minus, that's a plus. That's going to be a plus sign. These are going to cancel, so we're just going to be left with plus 2I sine n alpha. Is that it? How much you got? Okay. Find an expression in terms of alpha. All right, so we got that. Part D then. Show that, okay, so to show that, so that should be easy. Multiplying it by its conjugate, you end up getting cos squared plus sine squared equals 1. So that's fine. Hopefully you end up with cos squared with the alpha plus sine squared. So that does everything. So it holds. When you square them or multiply them, so that's okay. Hopefully you can get that. So part 2 then, write down and simplify the binomial expansion. All right, this. So W minus W conjugate binomial. I'll just do it out. I presume you have this shown. I'll simplify it a little bit. W to the power of 3 minus 3W squared W conjugate plus 3W W conjugate squared. Oh, I definitely should have that in brackets. Okay, minus W conjugate cubed. All right. I did some. I tidied this up a bit. Did it ask me to? Just make. That's why I did it. Okay, so I messed around. So I took out the 3W out of these. So a W cubed minus 3W, which leaves me with W times W conjugate is 1, which is 1. I took out. No, did I? No. Oh, I didn't. And this is then. No, yeah, so I did. And then I took out W conjugate here instead. And that's left with W times W conjugate, which is also 1. Minus W cubed. So that's gone 1 something. And then I can do something else. What was the other thing I did? So I factored out the 3. Okay, so we get W cubed minus W conjugate cubed minus 3 times W. Combine these with a common factor. Okay, I've tidied it up. These I need to write down simplified terms. No, I didn't. W and W cubed. I could have left it. I think I could have just left it as that. Couldn't I? I would have got full marks. Yeah, I think that's fine. Full marks. But I tidied it up because I saw what's coming next. Hence, show that sine 3 alpha. Talk me through what you did here, Sean, and where's the link here?
First thing is W part C, where there's 2 I sine of 3 alpha.
That's W, yeah, that's W1. Is it? No, that's W, sorry. That's, all right. W. Okay, so we need to use 3, yeah. So we W to the, so from part C, in part C, which I actually didn't write up here and probably should have, W to the N minus W. Yeah. We had that, didn't we? And that was
2 I sine N alpha.
and we know N. Oh, well, we need N to be. Yeah, so 3, I suppose. If you want to substitute N equal to 3, that would be W3 minus W conjugate 3 is equal to 2I sine 3 alpha. And of course, that is part of, that's that part, isn't it? Yeah. Okay.
And then the other part has to be
yes. So we also need N equal to 1 of this expression. W1 minus W conjugate 1 is equal to just 2I sine alpha, isn't it?
Yeah.
So that's going to be 3 times that. Okay. Let's just continue that up here. So I'm going to rewrite this using these. Two. Wow, this is confusing. 2 sine 3 alpha from this to replace that. Now I'm going to replace minus 3 times 2I sine just alpha. Now what does that equal?
That equals
Okay. Do we not need that in some form of sine? So it's you wrote that? Okay, that's the correct. Okay, so that's using all our hences. Now we got to make it look like the thing. That's 6I sine alpha. We got to make it look like something, but they have written no and show that. Yeah, so so how do I make it look like that? So that's gonna be okay. So that's gonna be minus 8I sine alpha equals. Oh yeah, sine cubed alpha equals. I forget what we're trying to. Is it just dividing by 2? Oh, you have to rearrange. So 2, yeah. So I can divide by 2 and then rearrange it. Is that, and then it just works, isn't it? Okay, divide everything by 2, and I want the cubed here. So I divide it by 2. That's 4I sine cubed alpha. That's that moved to there. Divided by 2. What did I want to sine 3? This one divided by 2. That'll be I sine 3 alpha. Oh, they're all i's. Don't need i's. I divided by 2I. And then minus 3 sine alpha. Oh, no, that's wrong. 4. What? What? No. That's minus 4 sine cubed alpha, which is the one I need to move. This goes over and that's there. Yes. 2, that's already divided. Sine 3 alpha, and that's the one that moves over. Oh, 3 sine alpha. Done. Okay. Goodness for that. That took me ages as well when I did it. And part E. Are you still stuck on it? Oh, I think I figured it out anyway. Let's do it. Okay, so is it hence salt? Hence salt. I'll do it up here. Don't think so. But this I'll just write it again. Which colors? How much time? Okay, so we have hence solve this 4. Oh, it's time to sign up. But hold on, now let me rearrange this. Let me multiply that out first. 4 sine cubed alpha plus 2 cos alpha sine alpha minus 3 sine. All right, so it is looking a bit like we just did. Let's make it look like we just did. So if 2 cos alpha sine alpha equals 3 sine alpha, if I rearrange that, sine cubed alpha, just bring it over and all that kind of jazz. That's the known one, isn't it? That's sine 2 alpha. And what's this from the other one? Sine 3 alpha. Okay, you're there. That means 2 alpha equals 3 alpha. Okay, so 2 alpha equals 3 alpha. It does. So one of my answers for alpha has got to be 0. Okay. And pi.
Well, that's a power of the, yeah.
Now, what does that? Yeah, pi does work. Yeah. So we can say it's pi. There's another 2. Think of rotation. Oh, jeez. It's gone. So it'd be. Can I write that? Well, this is what I wrote. I wrote that 3 alpha is then k rotations of pi minus 2 alpha. Because any sine alpha, make sure I get this right, is equal to pi minus. Because of sine's relationship, 30 and 150, that kind of thing. So can that help us? Alpha then would be from that k pi over pi. Yeah. Okay. What values can k be? Yeah. Oh, yeah. Can it be too many answers? Yeah. Can only be odd values of k. After it can be 0, 1, 3, 5. So 5 gives us pi. Why can it only be 1 and 3 and not 2 and 4?
Because it has to be on without k pi. Those are going to be 2 pi minus alpha because that's not minus.
Yeah.
Okay.
So you can't have 2 pi, it's just for pi. So what's my 2 other angles? So k is 1, and k is 3, and k is 5, we already have. You could have done 5 pi over 5 as well. Anything outside that, given by the question, which has disappeared off the screen, it was outside the range of values, so we need it. And that is that. Wow. Yeah. If you're able to do those questions, all those questions I gave you over the last 2 days, you should be absolutely fine for complex numbers. It is really, yeah. They're highly intertwined. As in, when you see a hard trig question, you're just going to have complex numbers in it. All right, let's stop. So, what's coming up? IA, we have your deadlines now. Your actual draft is going to be on the 11th of January, which is the Monday after we come back. That's your actual draft. And the actual one then needs to be in on the 4th of February, which is that Friday. That's plenty of time still. The other thing is the last 3 lessons of this term is you're going to get 3 papers. I don't know, did I say? I said your first attempt at a full mock. So we'll see how that goes. So that will be, I think, I need to confirm whether Wednesday afternoon on the last day of school is going to be a lesson. I don't know if they're going to finish that day early or not. I can't. So if they finish it, once we confirm that, if they finish early, that means the last paper would have to be on the Tuesday. The previous one would have to be on the Friday. That would be paper 2. Paper 1 won't be the Wednesday because we have a day off next Wednesday. So it would have to be the next lesson. Oh no, sorry, Friday we still have, but then the first lesson next week would be your paper 1. I think we probably have to go with that just in case. And then if we do have this double lesson on the last day, we'll just go through the answers. So that's the plan. What we look at on Friday is polynomials. And I'll send you some functions on polynomials together. So like, polynomials will be fine now, yeah. So I'll try and set you some difficult ones, but I might give you, actually I just finished polynomials and functions with year 12, so I might give you their practice test and some to test just to see how you get on. Well, hopefully you will. All right, sweet. Let's stop recording, and hopefully tomorrow I'll watch this back. That'll be the test. Tomorrow, what was the sauce in the recording? If you watch the full thing, you will know what